Here we're going to talk about covalent chemical bonding and how that pertains to these Lewis structures, what happens when we have now multiple bonds, and comparing that to what we had previously talked about, which was the ionic bonding system. So again, these Lewis structures, when these compounds form between elements with more similar properties, electrons aren't transferred from one element to another, but instead are shared. Which is what we're familiar with already when we have covalent bonding. They, instead of transferring an electron from one to the other, forming a cation and an anion, they're shared between the two. So this Lewis theory of bonding is assuming that these electrons are shared in a chemical bond. So this is what one of these can look like. So you have hydrogen, it has one valence electron. You can combine those together. And it ends up looking like this, where you have the two hydrogens next to each other. Those two electrons are a chemical bond, and they're being shared. This will sometimes be depicted as a line. And in fact, I would say more commonly is depicted as a line, but that is representing two electrons. Each hydrogen atom, you end up counting both of those electrons as its own electrons. So that means that those hydrogens feel as though they are like that noble gas configuration. In this case, it's helium, so there's just 2 electrons instead of 8 electrons, so it's a duet instead of an octet. So covalent bonding, these two atoms share a pair of electrons, and a covalent bond is that actual shared pair of electrons. So the octet rule, atoms lose, gain, or share electrons to achieve a noble gas electron configuration. There are some important exceptions to the octet rule. In fact, there are a lot of important exceptions to the octet rule. It probably shouldn't be called a rule. It's more of a guideline. Here's one example of how this octet rule would function. So if you have fluoride, you have 2 fluorines that are coming together. They both have 7 valence electrons. In order for them to both totally be satisfied in terms of having 8 valence electrons total, which is the octet rule, they can both share their 1 lone valent electron of their 7 to form a chemical bond between the two. So you have these 2 shared electrons that you can now convert between showing as 2 dots to drawing a line. Again, that's going to be more commonly shown. The electrons that are not engaged in chemical bonding are called lone pairs. So lone pair of electrons. They're alone and they're a pair of electrons, and they are localized on that individual atom. They are not engaging in chemical bonding, even though they are valence electrons for that individual atom. It's only the electrons that are being shared between those 2 fluorines in order that we would call a chemical bond, a covalent bond in this case. Structures used to represent molecules held together by covalent bonds, such as H2 and F2. This is when we can use Lewis structures most appropriately. You had seen previously that we can use Lewis dot structures for ionic bonding. It is not as common to show that. Mostly Lewis dot structures are used for covalent bonding. So they're just, again, these representations of covalent bonds where you're sharing electrons. Where we're showing those as a dash between the two. Originally they were dots, but we tend to convert them to dashes, which is that chemical bond. So here's H2O, water. You can show that kind of traditional Lewis dot on the left-hand side there, or more appropriately, you're going to see it far more common. We're converting those 2 shared electrons to lines, but that oxygen still has 2 lone pairs, so you'd leave those on there. In dealing with the octets of these individual atoms, again, take a look at our prior example of F2, fluorine. Both of those fluorines have a filled octet. Remember those 2 electrons in the center that are the covalent chemical bond? Those are being shared, so they are considered a part of both of the octets of both the first fluorine and the second fluorine. So you can see that both fluorines have a completely filled octet. They have 8 valence electrons, since those 2 in the center are being shared. Likewise, hydrogen, remember, only needs 2 electrons. So it does have its filled duet, it's filled 2 electrons, and then oxygen again will have 8 here. It starts off with 6 valence electrons, but it ends up sharing some electrons with each of those hydrogens because each hydrogen has 1 electron to get a full octet for oxygen. So this is how we can show covalent chemical bonding with this Lewis dot structure system. So single bonds are what we've seen so far, where 2 atoms are held together by 1 electron pair, and that's where we are showing one line, which is a single bond. There's also multiple bonds. They form when 2 atoms share 2 or more pairs of electrons. So a double bond is it's a type of multiple bond in which you are sharing 2 pairs of electrons, and a triple bond is 3 pairs of electrons. So a triple bond is 6 electrons total. A double bond is 4 electrons total, and a single bond again was just those 2 electrons total. You can get higher than this within reason, though. For covalent bonding, you're only going to be concerned with up to a triple bond. Okay, so this is what one of those would look like. For example, here we have CO2, carbon dioxide. And in order to get the filled octets of all of those, you end up sharing more electrons between the carbon and oxygen than what you had previously. So that carbon has 8 electrons, each oxygen has 8 electrons, so they're all obeying that octet guideline or octet rule. We'll learn how we can determine that this is how it should be, but it's to try and honor that 8 electron rule. So you end up getting a Lewis dot structure that has 4 electrons being shared between a carbon and an oxygen, and another 4 electrons being shared between the carbon and the other oxygen. So those will be represented as 2 lines, which is a double bond. So each carbon-oxygen has a double bond associated with it. We can do a similar sort of thing for C2H4, where we're getting a carbon-carbon double bond. There are 4 electrons that are being shared between those. And you can again see that all of these carbons are respecting the 8 electron rule, each hydrogen having 2. Another example would be that nitrogen for N2. N2, remember nitrogen was a diatomic in nature, so N2 is fairly common. Nitrogen gas, for example, N2 gas, actually has a triple bond between those 2 nitrogens. Each nitrogen has 5 valence electrons, so in order to get each of those nitrogens to have 8 total electrons, they each need to share 3 with each other. So that gets you 6 total electrons that are being shared between those 2 nitrogens, which is what we call a triple bond. So we're drawing 3 dashes between those 2 nitrogens, indicating a triple bond. Each of those nitrogens still has a lone pair in order to get a total of 8 electrons. So this would be how you draw that Lewis dot structure for nitrogen. You can see there's another example where carbon is forming a triple bond. Bond length also really matters in terms of multiple bonds. So the bond length is defined as the distance between the nuclei of 2 covalently bonded atoms in a molecule. Multiple bonds tend to have shorter bond lengths than single bonds. There are more electrons there. So just in taking a look, you have carbon monoxide, 1.13, N2, which is 1.10. So nitrogen for N2 is N2 gas, and that was a triple bond. It's a very strong bond, so it's a very short bond. So this also pertains to strength. So multiple bonds tend to be stronger, and they tend to be shorter than single bonds. And you can see some trends on the side. If you compare carbon-oxygen single bond to carbon-oxygen double bond to carbon-oxygen triple bond, you see it goes from 143 picometers to 121 to 113. So we're getting progressively shorter bond lengths as we get higher and higher multiple bonds. So going from a single to a double to a triple bond. Again, picometer was just 10 to the negative 12th meters. So it's one farther than nano, where nano is 10 to the negative 9th. And I know we hadn't talked in the past about 10 to the negative 12th meters, picometers, but this is a common unit for bond lengths since bonds are such short distances. Picometers actually tends to be the preferred unit for bond lengths. So here's some just general comparison of the covalent bonding to try and compare covalent compounds to ionic compounds. And we've talked about this before, but they will have very different physical properties because of how very dramatically different the nature of their bonds are. Where covalent bonding, we have that sharing of electrons. We're not forming positive and negative cations and anions like we are in ionic compounds. Covalent bonds tend to actually be a little weak in comparison to ionic bonding. As a result, they tend to not, their physical properties are very different. So they tend to be gases, liquids, or low melting solids. So very low melting points for these solids. And you can read the other differences where ionic compounds, they have very strong these ions are held together very strongly. And they tend to be solids at room temperature and have very, very high melting points. It takes a lot of energy to break them apart. That's what we had talked about with lattice energy. And these ionic compounds tend to be soluble in water. Many of them are, as we've been familiar with in the past. Since covalent compounds are not forming ions in solution, very rarely do they conduct electricity if they are dissolved in water, for example, which they often do not dissolve in water. Where these ionic compounds, if they're dissolved in water, we know that they become strong electrolytes, so they can conduct electricity. And even if you do melt an ionic compound, which is very hard to do, but if you do that, that will also conduct electricity because they have these mobile cations and anions. So there's some pretty marked differences between these two. Here's just a brief example of a difference, some of the physical properties between these two. So here you have sodium chloride, which is a representative ionic compound, and here's a covalent compound, carbon tetrachloride. And you can see in their appearance, sodium chloride we know is a white solid. This is table salt. Carbon tetrachloride is a colorless liquid. You can see there's very different melting points. Sodium chloride takes 800 degrees Celsius to melt, where you can get carbon tetrachloride to be a solid, but it's at below negative 23 degrees Celsius. And you can see differences in boiling points, solubility in water, high versus very low, and electrical conductivity. Carbon tetrachloride is always bad, where sodium chloride as a solid, it isn't a good conductor because those ions are totally immobilized. But once it's a liquid or dissolved in water, it becomes a very good conductor. So here are some basic differences between these two.